My name is Kacie, and I was a mathematics research student for the CORE program, which stands for Collaboration on Riverine Ecology. Altogether, there were 4 students. We were placed into groups with one other person. Each pair had 1 math student and 1 biology student. Now let's take a closer look. Bithynia tentaculata is an invasive snail that is native to Europe. It has been in the Great Lakes since the 1800s, but recently, around 2002, has been introduced into the upper Mississippi River. Bithynia tentaculata serves as the first intermediate host of the parasitic flatworm Spiridia trima pseudoglobulus. After the parasite is harbored in the snail for some time, the parasite enters its cercarial stage of its life cycle. Consequently, the snail begins to shed these cercaria, which can then reinfect Bithynia as well as native snails, and both can serve as the second intermediate host. The waterfowl then consume these snails and in turn serve as the definitive host, and thus continues the cycle. Even though a snail is infected with the parasite, the snail can continue living its entire lifespan of about 3 years without dying from this infection. However, the parasite will castrate the snail. But sadly enough, when the waterfowl come into contact with an infected snail, exposing it to the parasite, the bird will typically die within 3 to 8 days. This has been causing extreme amounts of waterfowl death every year since Bithynia tentaculata was introduced to the upper Mississippi River. But unfortunately, little information is known about this system. In order to someday, hopefully in the near future, understand the system as a whole, it is necessary to break the system down into its most basic parts. Understanding the host-parasite interaction is a very important component to understanding the system. The snails in our experiment were split into 2 categories, non-infected and infected Bithynia tentaculata. Each individual snail had its own cup. They were fed ad libitum and the water was changed twice a week. Twice a week, measurements of mass, length, and volume were taken of each snail. With the help from the data we collected in the lab, we were able to take a look at the differences in energy allocation in infected Bithynia tentaculata compared to non-infected Bithynia tentaculata. The energy allocation of the snail can be broken down and directed toward 4 major components: growth, maintenance, reproduction, and parasite. We then can apply this concept to a dynamic energy budget model, or DEB model. The DEB model consists of a system of differential equations that will help us determine the energy allocated to each component. Looking at the comparison of the non-infected snail versus the infected snail, we will get a better understanding of how the snail is affected by the parasite, whether it be a difference in physical size or if it burns out more or less energy for maintenance, etc. With the collaboration of mathematics and biology, we have been able to depict a more accurate model in order to get a better understanding of this system.